you are probably completely confident about one thing: the universe is enormous, and distance in space is a real, measurable fact. Astronomers tell us the Andromeda Galaxy sits about 2.5 million light-years away. The nearest star beyond our solar system is roughly 4 light-years away. These numbers appear precise, scientific, and reliable. They seem like permanent features of reality itself. But what if the idea you have about distance in space is deeply misleading? What if distance is not a fundamental property of the universe at all? In this video, we are going to explore a surprising and unsettling idea from modern physics, that the distances we measure across the universe might not be truly fundamental. Before we continue, make sure to subscribe to the channel and click the bell icon so you don't miss future videos exploring the strange and fascinating ideas hidden inside modern physics. Now let's begin with something that seems obvious. Distance feels like one of the most basic ideas in existence. The moon is roughly 250,000 miles away from Earth. The sun sits about 93 million miles away. These numbers appear solid and permanent, like coordinates written into the structure of reality. Distance, after all, simply means how far apart two things are. It sounds almost too simple to question. But in physics, the concepts that seem simplest often hide the deepest mysteries, and distance turns out to be one of them. What most people don't realize is that when astronomers measure cosmic distances, they are not actually measuring distance in the way we imagine. Instead, they are measuring time. Take the Andromeda Galaxy as an example. When scientists say Andromeda is about 2.5 million light-years away, that sounds like a distance measurement. But a light-year is not actually a unit of space. It is a unit of time converted into distance. A light-year simply describes how far light travels in 1 year. So when astronomers say Andromeda is 2.5 million light-years away, what they are really saying is this: the light we are seeing from Andromeda left that galaxy 2.5 million years ago. In other words, when you look at Andromeda through a telescope, you are not seeing the galaxy as it exists today. You are seeing it as it existed millions of years in the past. This creates a strange problem. The galaxy you see is not where Andromeda is now. It is where Andromeda was when that light began its journey across the universe. During the 2.5 million years that light traveled toward Earth, the galaxy itself continued moving through space. That means the distance we measure is not the present-day separation between us and Andromeda. It is the distance the light traveled through space during those millions of years. But the situation becomes even more complicated. While light travels across the cosmos, the universe itself is expanding, stretching the space between galaxies. This means the distance light traveled isn't the same as the distance separating us from those galaxies today. There is no single correct answer. Einstein's theory of special relativity changed everything. It showed that space and time are not absolute. They depend on how fast you're moving. As you approach the speed of light, objects physically contract in your direction of motion. A ruler's length actually changes based on your perspective. At 99% of the speed of light, an object shrinks to just 14% of its original size. At the speed of light itself, length effectively vanishes. Distance isn't just a number on a page, it's a relative measurement. Now think about what this means for our place in the universe. If you remain on Earth observing the Andromeda Galaxy, you measure the distance to be roughly 2.5 million light-years. But imagine that you board a spacecraft traveling toward Andromeda at 99% of the speed of light. From your perspective, the distance would no longer be 2.5 million light-years. Because of length contraction, the distance along your direction of motion would shrink dramatically, compressing to roughly 350,000 light-years. You and an observer on Earth would measure completely different distances to the same galaxy, and yet both measurements would be correct. Each observer is using a valid reference frame. This is one of the most surprising consequences of Einstein's theory. Distance is not absolute. The concept becomes even more extreme for light itself. A photon travels at the speed of light, experiencing the maximum possible length contraction. From the perspective of the photon, the distance to its destination shrinks to zero. For light itself, the entire universe has no size. Distance depends entirely on motion. What seemed like a simple measurement is now something that depends on your frame of reference. But relativity does not stop there. Einstein later realized that space itself is not rigid. It is flexible and dynamic. Space and time form a flexible structure called spacetime, which can bend, stretch, and curve in response to matter and energy. The presence of a massive object, like a planet or a black hole, changes the geometry of the space around it, and thus the distance itself. This means distance is not determined by a fixed background grid, but by the very shape of space-time itself. Imagine a heavy ball on a stretched sheet of rubber. The sheet dips, changing the path and the distance between any 2 points. In curved space-time, the shortest path between 2 points is a geodesic. Objects moving under gravity simply follow these curved paths. In Einstein's universe, distance is not a fixed property, but a beautiful dance between motion, matter, and the curvature of space itself. Distances in space depend on space-time curvature. Change the distribution of matter and energy, and you change the geometry and the distances between objects. Black holes are the ultimate example. From the outside, they have a set size defined by their event horizon. But inside, space-time warps so much that the interior can hold an enormous, almost infinite amount of space. This reveals that distance is not a fundamental block of space. It's a derived concept shaped entirely by the geometry of the universe. But the story goes deeper. In the quantum world, our classical picture of space and fixed distances breaks down entirely. Particles can become entangled, connecting in ways that ignore spatial separation. Here, the very concept of distance begins to dissolve. Space is far more mysterious than it appears, and distance is just the beginning of the story. Quantum entanglement occurs when two particles interact in such a way that their quantum states become linked. After this interaction, the particles can move far apart, even across vast cosmic distances, yet they remain part of the same quantum system. Instead of having independent properties, their behavior becomes correlated in a precise mathematical way. If you measure a property of one entangled particle, such as its spin, you immediately know the corresponding property of the other particle, no matter how far away it is. This puzzled Albert Einstein deeply. He famously described it as spooky action at a distance. Einstein believed that there must be some hidden explanation that preserved the classical idea of local reality, where influences could not travel faster than light. But decades of experiments have confirmed that entanglement is real. Scientists have repeatedly demonstrated entangled particles separated by large distances. Scientists have repeatedly demonstrated entangled particles separated by large distances while maintaining perfect correlations between their measurements. Two particles can be separated by kilometers, by planets, or even theoretically by billions of light years, and their quantum relationship remains intact. This leads to a remarkable conclusion. From a quantum mechanical perspective, spatial distance does not break the connection between entangled particles. Two particles that are extremely far apart in space can still behave as parts of a single quantum system. Meanwhile, two particles sitting right next to each other may have no quantum connection at all if they are not entangled. In other words, spatial distance and quantum closeness are not the same thing. Two objects can be far apart in space, yet deeply connected in quantum terms. And two objects can be physically adjacent while being completely unrelated. This observation hints that the structure of space might not be the most fundamental layer of reality. Something deeper may determine how parts are connected. This idea became dramatically clearer in the late 1990s when physicist Juan Maldacena proposed one of the most revolutionary discoveries in modern physics. In 1997, Maldacena introduced a powerful mathematical relationship known as the ADSA-CFT correspondence. This relationship showed that two very different types of physical theories could describe exactly the same reality. On one side of the correspondence is a theory of gravity existing within a curved space containing three spatial dimensions. On the other side is a quantum field theory living on the two-dimensional boundary of that space, with no gravity at all. Despite the difference in dimensions and physical description, the two theories produce identical predictions. Every event described in the gravitational theory corresponds perfectly to something happening in the boundary quantum theory. This discovery gave rise to what physicists now call the holographic principle. The holographic principle suggests that a universe with three dimensions of space can be completely described by information stored on a two-dimensional surface surrounding it. In this picture, the third dimension, the depth that gives space its sense of distance, may not be fundamental at all. Instead, it emerges from the underlying quantum relationships in the boundary theory. Think about the implications of that. In the three-dimensional description, objects exist at different distances from each other. Gravity acts across those distances, and the geometry of space-time determines how objects move. But in the two-dimensional quantum description, there is no third spatial dimension. There is no depth, and therefore no distance in that direction. Instead, what corresponds to distance in the three-dimensional universe becomes something entirely different in the quantum theory. It corresponds to energy scale. Processes that occur close to the boundary in the gravitational description correspond to high-energy interactions in the quantum theory. Processes deeper within the space correspond to lower energy scales. So what we perceive as spatial depth is actually a reflection of how quantum interactions behave at different energy levels. Distance in this framework is not a fundamental ingredient of reality. It emerges from the relationships between quantum states. Recent research has pushed this idea even further. Physicists studying quantum gravity have discovered strong evidence that space-time geometry itself may be built from quantum entanglement. The amount of entanglement between different parts of a quantum system appears to determine how space-time is stitched together. Regions that are strongly entangled correspond to areas of space-time that are close together. Regions with weaker entanglement correspond to areas that appear farther apart. In other words, distance may actually be a manifestation of quantum entanglement. The fabric of space itself could be nothing more than a network of quantum connections. Remove the entanglement between two regions of the system, and the geometry of space-time separating them grows larger. Increase the entanglement, and those regions become closer in the emergent geometry. In extreme cases, removing entanglement entirely could cause space-time itself to split apart into disconnected regions. Space would literally fall apart if the quantum connections that hold it together disappeared. At this point, the familiar idea of distance as a fundamental feature of the universe begins to dissolve completely. Instead of being the stage on which physics happens, space may actually be something that emerges from deeper quantum relationships. And the deeper physicists investigate this possibility, the more it seems that distance may only be a large-scale illusion created by the quantum structure beneath it. If the idea that space-time might emerge from quantum entanglement sounds radical, the implications become even more striking when physicists explore what happens when entanglement is gradually removed. One of the clearest demonstrations of this idea comes from work by theoretical physicist Mark van Ramsdonk. One of the clearest demonstrations of this idea comes from work by theoretical physicist Mark van Ramsdonk. His research showed that the connectivity of space-time itself may depend directly on the amount of quantum entanglement between different regions of a quantum system. To understand this, imagine the quantum description of a universe represented by a large network of interacting quantum states. In this description, the amount of entanglement between different parts of the system determines how those parts relate to each other. Strong entanglement creates tight connections between regions, while weak entanglement produces looser relationships. Van Ramsdonk considered a thought experiment. What would happen if we took the quantum state describing a region of space-time and gradually reduced the entanglement between two halves of it? The answer turned out to be extraordinary. As the entanglement decreases, the geometry of space-time linking the two regions begins to stretch. The distance between them increases. If the entanglement continues to decrease further, the separation grows even larger. Eventually, if the entanglement is reduced to zero, the two regions become completely disconnected. Space-time literally splits into two separate pieces. In this framework, the connection between regions of space is maintained by quantum entanglement, not some underlying background geometry. This leads to a remarkable insight. Distance is not something that exists independently. It is a reflection of how strongly different parts of that system are entangled. In other words, the geometry of space-time, including the distances between objects, is built from patterns of quantum entanglement. Another development that pushes this idea even further is the Brown-Strauss EPR conjecture, proposed by Juan Maldacena and Leonard Susskind. The first concept is the Einstein-Rosen bridge, or a wormhole, a hypothetical tunnel through space-time that connects two distant regions. The second concept is the EPR pair, two particles that are maximally entangled, meaning their quantum states are deeply linked regardless of separation. The EPR conjecture proposes that these two ideas are actually two descriptions of the same phenomenon. According to this conjecture, when two particles are maximally entangled, they are connected by a kind of microscopic wormhole in space-time. This wormhole does not allow information to travel faster than light, but it represents a geometric connection between the two particles. From this perspective, entanglement and geometry are not separate phenomena. They are different ways of describing the same underlying structure. If this picture is correct, the universe is not simply empty space. It is a complex quantum network where everything is linked through patterns of entanglement. Another approach, loop quantum gravity, leads to a similar conclusion. Space-time is composed of discrete units known as spin networks. In this framework, the nodes represent volume and the links represent area. The geometry of space arises from how these nodes and links are connected. Distances in the universe are not infinitely divisible. They come in discrete units related to the Planck length, about 10 to the power of minus 35 meters. Below this scale, the concept of distance simply stops making sense. It's the absolute limit of our physical geometry. Just as temperature emerges from the collective motion of molecules, distance emerges from the statistical behavior of the underlying quantum structure of space-time. At everyday scales, space appears smooth and continuous, but this geometry may only be an approximation. At the most fundamental level, space-time may not contain distances at all. Instead, it consists of a network of quantum relationships. Distance might simply be the way our large-scale perspective interprets deeper quantum connections. In quantum physics, states can become entangled, forming connections that do not depend on ordinary spatial distance. From the viewpoint of classical physics, particles appear far apart, but in the quantum system, they are part of the same structure. Space is not the primary framework of our universe. It is the pattern of relationships between quantum states. In recent years, physicists have explored this idea in increasing detail. Research into quantum gravity suggests that the geometry of space-time, including its distances and curvature, may arise from the entanglement structure of the underlying quantum system. In this picture, space-time behaves like a fabric woven from quantum links. Each connection between parts of the system contributes to the overall structure of the universe. Regions that are strongly entangled appear close together in space. Regions that share weaker connections appear farther apart. The geometry we perceive as space is therefore a macroscopic description of those microscopic relationships. When enormous numbers of quantum interactions are averaged together, the result looks like a smooth three-dimensional world with measurable distances. But the deeper reality may not contain those distances at all. Another fascinating aspect of this idea is how it changes the way we think about the size of the universe. Cosmologists often describe the observable universe as being about 93 billion light years across. That number seems unimaginably large, stretching far beyond anything humans can directly experience. Yet this vastness exists within the framework of classical space-time geometry. It is a measurement that assumes space itself is fundamental. If space-time instead emerges from a deeper quantum structure, the apparent size of the universe becomes a property of that emergent geometry rather than a basic feature of reality. The true description of the cosmos might not involve billions of light years of empty space separating objects. Instead, it may involve a complex network of quantum states whose relationships give rise to the illusion of spatial distance. This does not mean that the universe suddenly becomes small or that we could travel instantly between distant galaxies. The physical laws governing energy, causality, and information still impose strict limits on what can happen. Quantum entanglement, for example, does not allow faster-than-light communication. Even though entangled particles remain connected in a quantum sense, that connection cannot be used to send information instantaneously across space. The classical rules of relativity still apply to signals, matter, and energy. What changes is not the practical behavior of the universe, but our understanding of what space actually is. Instead of viewing the universe as a giant container filled with objects, we begin to see it as a dynamic system of relationships. The connections between quantum states form the foundation, and space-time emerges from those connections when viewed at large scales. This shift in perspective is similar to the way matter was transformed. Centuries ago, people believed that matter was made of solid, indivisible particles. Later, scientists discovered that atoms contain smaller components, such as electrons and nuclei. Eventually, those particles were understood as excitations of underlying quantum fields. Each step revealed that what seemed fundamental was actually an emergent layer built on deeper structures. The same process may now be happening with space itself. For thousands of years, humans assumed that space was the permanent stage on which the universe existed. But modern physics suggests that space may not be the stage at all. It may be the result of deeper processes at the quantum level. Distance then becomes like a convenient language we use to describe those processes and navigate the world. But it may not represent the true structure of reality any more than temperature represents the motion of molecules. Galaxies may be part of a single interconnected quantum system whose relationships generate the geometry we perceive as space. What appears as a universe separated by light years may be a unified quantum reality where distance simply does not exist